So, hello, good morning, everyone. It's a small group, so let's keep it informal and interactive. I would like to talk about the homomorphic encryption. Sounds like a mouthful, but it's a really exciting development in cybersecurity. And I'm sure everyone on this call doesn't need to be reminded of all the cyber attacks that we have been facing. Um, there's a statistic that every 11 seconds there is a cyber attack occurring, right? And not to sound alarmist, but none of us are safe. So, um, as you can see from this moving GIF picture, what it's trying to show is that data normally is encrypted while it is either at rest, so like for example, laying in your hard drive or in your server's memory, where it is encrypted by, let's say, advanced encryption systems, which is a well-known encryption or algorithm, or while it is on the wire, which basically means while it's on the network, right? Where you have, of course, your SSL and TLS. What's lacking is encryption while you're actually working on the data. And that is becoming increasingly important given all the phishing attacks, the cross-site scripting attacks. For example, if you're working on something important or crucial on your laptop, you have another website open, let's say on your browser. Uh, there's something called a cross-site scripting attack where the malware can actually cross over and actually take the information from what you're working on your laptop, and you actually won't even realize what's happening, right? Imagine if while you're working on the data, it's all encrypted. So it doesn't matter whether it's at rest, it's you're working on it, or it's on the wire. You can basically breathe a sigh of relief. So this is what homomorphic encryption is all about. I'll just cover very briefly a small and short intro to cryptography, because after all, this is a cryptography topic. A very short breakdown and easily understandable bit of maths around homomorphic encryption, some of the use cases, and then I will introduce a toolkit with which you can get started almost immediately within the next few minutes, working on playing around with some Python and working on some use cases. So without further ado, let's get started. Brief history of cryptography. Julius Caesar is probably the most well-known pioneer of encryption, what we call symmetric encryption. Symmetric encryption is nothing but when encryption and decryption uses the same secret key. So what Julius Caesar did is when he communicated with his troops and he used a code where he simply rotated his alphabet by 3 places. So for example, an A would become a D would become a G, H, and so forth. This is called the Caesar cipher, and it's actually one of the precursors of encryption as we know it today. On the right, you can see another so-called historical example. Those of you who are fans of Benedict Cumberbatch, I'm a huge fan. Do check out this movie called The Imitation Game, which was released in 2014, where Benedict actually plays Alan Turing. So Alan Turing, as many of you guys may know, is very famous not only in the AI space but in the crypto space as well. And those were World War II days. So remember that Germany and the US, they were on the opposite side, the Allies and the Axis powers. And Germany actually used this machine called the Enigma, which you can see on the top right. It is actually nothing more than a machine which makes this symmetric encryption process a bit more sophisticated. So what Alan Turing did, he used information theory to break the Enigma code. So for those of you who are interested, do check out this movie. Moving on to 1970s, these names may not be unfamiliar to technical experts such as yourself. RSA, so Rivest, Edelman, and Shamir, Merkel, Helbin, and Diffie, these are the guys who actually invented what is known as asymmetric encryption and the key exchange algorithms, which is basically the basis for all the network encryption we see today. So what's the difference between symmetric and asymmetric? It's very simple. Symmetric uses just one key for encryption and decryption. Asymmetric uses a pair of keys, a public key and a private key. So just to note, here we finished the historical portion, but this actually has a key bearing on the development of homomorphic encryption today, and we'll see how. So let's talk about asymmetric encryption. So when we scroll to websites like Amazon, Google, IBM.com, we see HTTPS. With the S after the HTTP, we are assured, right, that this is protected by SSL or TLS, and that is basically asymmetric encryption in action. On the right, you don't need to worry too much about the maths, but this is actually the formula for the RSA asymmetric encryption algorithm we discussed. I think the major portion that we should note is the randomness. So every time this pair of keys is calculated, every time messages are encrypted and decrypted, there is a certain amount of randomness created. Because we always use, these algorithms use random numbers such as products of two integers, an encoding exponent, a decoding exponent. So the more and more encryption algorithms run throughout computer operations, the more randomness is introduced into the system. And just take note of that because it does have a bearing on how homomorphic encryption came to be. So computing on encrypted data, some people, the mathematical geniuses did note that the RSA algorithm actually does have an element of multiplicative homomorphism. And what do I mean by that? Again, don't get bored or by the maths on this slide. It simply means that when you multiply the ciphertext, when you multiply, let's say, the left-hand side of the equation, the right-hand side of the equation, which is the encrypted and the plain text, is also multiplied. So homomorphism in algebra means nothing but like a mirror between two functions. So if the left-hand side undergoes a certain operation, the right-hand side will also undergo the same operation. And that's why we call this homomorphic encryption. So again, if you see on the left, you break down the RSA algorithm, you will find that it is multiplicative, but not additive. Whereas other encryption schemes were additive, but not multiplicative. So the question you may have is, why do we need both? Why do we need sums and products? And the answer, to break it down as simply as possible, is this. The two key operations in our computing is XOR and AND. These are the two key computing operations that we have in all our computing, right? And XOR and AND is nothing but multiplication and addition. So what this actually means is if we want a truly effective homomorphic encryption algorithm, we have to have both sums and products. So this is a bit of the math to get you a bit curious on this topic. So what did people actually want? What people wanted was the ability to compute on encrypted data with both sums and products. And this is what Craig Gentry actually came up with in 2008 and gives us a bit of pride to say that Craig was actually an IBM researcher. And he found a way to create the homomorphic encryption algorithm in such a way that both sums and products were covered and the randomness was reduced. So he actually started this whole revolution, what we call the first generation of HME. And after that, we have the second, third, and I think currently we are at the fourth generation. So what is this concept of noise in ciphertext? So remember we spoke about randomness earlier in the RSA algorithm. So the key fact is if there is too much noise in the ciphertext, then when you decrypt it, the result will actually be incorrect. So there is actually a threshold which you can see on the left-hand side. If there is too much noise, it will lead to incorrect decryption. So the noise has to actually be below the threshold. And remember, noise here is nothing but randomness. So as the algorithms are calculated, there are a lot of random numbers involved. And as it proceeds down the computer line, this randomness actually increases. So we needed a way to control this noise, which is exactly what Gentry did. So Gentry invented a concept called bootstrapping. What bootstrapping is that instead of having just one key with a whole lot of noise, he introduced a second key, which on this slide is covered with the red and blue boxes. This second key was calculated such that it counteracted the noise which was already generated by the algorithm. So when you decrypt the portion which has been encrypted by the noisy key, the second key also does a decryption to counteract the noise that has been produced by the homomorphic encryption. So don't get confused by all these fancy terms. It basically means that they introduced the key with less randomness when the key was created so that it counteracted the randomness which actually existed in the algorithm already. So I think we've covered enough of maths. Now let's go into a bit more practical stuff. how will this actually change the world? So we have a lot of data being passed to third-party cloud providers, IBM, AWS, Azure, offshore computing services, data centers which are not on-premise. And this may include really critical data such as health data, blood work, your diseases, your genomic data, tax data, crime prevention, of course, financial data, your financial records, credit card, etc., right? So there is always a concern when all this data goes to third-party clouds or computing services which are actually not on your premise. How do you actually ensure it is safe? And homomorphic encryption is the answer. Because remember, it means that even when the data is being computed upon in the third-party clouds, it will still be encrypted. And so if data breaches actually do occur, the cyber attackers will actually gain nothing at all because they would not be able to unscramble that data. So this is already happening. There are already some use cases underway. Let's take one example of a credit card fraud detection. So you will actually find this in the toolkit I will introduce a little later. We all know that credit card fraud is costing billions of dollars, and COVID-19 has actually worsened this. So it's very difficult for a bank, for example, to find out what is fraud and what is not fraud because of the effect of this pandemic. So where FHE actually comes in, it can perform encrypted AI inferencing. So those of you who are familiar with AI and machine learning, FHE can actually encrypt your entire neural network, the hyperparameters, the weights, so that everything is protected, right? And you can see that this will help you support a zero trust strategy and unlock the value of your personal data without actually gaining exposure to that data. So that this is a very good use case which we can get started with right away. Very simple how FHE actually works, coming down from the maths to the computing side. You encrypt the data. Those of us who possess the FHE toolkits and capabilities, computation is performed, and then we decrypt that data with the key that we have. So again, it keeps sensitive data encrypted at all times, securing the cloud for highly regulated industries. Big players like Microsoft, like IBM, all of them are coming out with what is called confidential computing and cloud for financial and banking. FHE is being infused into all of these capabilities. But there are some caveats. So FHE is not as easy as click and go. It does require a significant amount of computing power. For example, when Gentry actually started his FHE operations, it took 30 minutes for him to encrypt just one bit. And you can imagine that that is absolutely impractical. So as we have proceeded through the ages, through the years, this has become more and more easier with the availability of computing power, the sheer processing power that we have today. And FHE, of course, has a lot of open source tools. We will explore one very shortly. And the good thing is that we can now actually run this on a host of platforms, including Linux, including even Mac OS or Windows as well. So how does this tie into the hardware discussion? So as most of you would probably know, last year, IBM came out with the IBM Power 10 line of servers. One of our talking points, if you will, is that we can perform all this encryption with no performance impact. So remember I said that FHE requires a high degree of computing power. Imagine if you can do all that with no performance impact to your application. This is the value that IBM Power 10 brings. And how does it bring that? We have 4x the number of crypto engines in every core, and our encryption is almost 2.5x faster per core compared to competitive platforms in the market today. So yeah, these systems which were released last year, it does have the capability to support fully homomorphic encryption and quantum safe cryptography. Going to the toolkit that I will be introducing, it's called HElayers. It's provided as an SDK. And for you Python aficionados out there, it includes a Python API. So data scientists and application developers can immediately get started on FHE with many use cases such as linear logistic regression. Remember the credit card fraud example we talked about that involves neural networks. As I said, it is highly portable. It works across Windows, Linux, and Mac OS. In fact, we are also exploring whether it can work on the IBM Power system itself. On the right-hand side, you can see the link to where you can actually access this toolkit. So now I will just move quickly to the toolkit itself so you can get a view of how it looks and you can start playing around. This is the package, the SDK, if you will. It consists of a series of notebooks in Python. So there is a getting started notebook and there is a FHE basics notebook. So in the basics, I will just go through a few steps to let you know how you can get started within a few minutes. The first thing you can do is just basically import the library. So FHE-Layers, as you would do in Python, for anything that any computing that you perform, you need to import the library first. You need to possibly import the utilities for the system. And then you create what is called a context. This context is actually nothing but the main FHE object. It will store your encryption keys, it will store your parameters, and it will initialize all the mathematical constructs. So you have to create the context, and you can see that in this piece of code. You set a few parameters such as the security level and the precision and the multiplicative depth. These are a few technical parameters that you need to set when you actually initialize this context. And then that's it. You're more or less set to start simple operations with FHE, such as addition, multiplication, and averaging the data. So for example, if you want to perform a simple addition, you just encode the vector, and then you can simply do a C1 plus add plus C2, and you get the result. So remember that you have already created the object. The object is doing all the work in the backend for you, and you would just basically code as you normally would in Python. And in this toolkit, you can see some other exercises that you can perform with neural networks, logistic regression, text analytics. So my only advice is to go and have fun with it, right? And last few slides from my end. This is the steps that you would follow to actually access the toolkit. You do need Docker because it is provided as a Docker container. You run the image, and then you just go and access this URL, and you will get to play around with whatever I showed you. So some further resources which you can use to explore. There's a developer blog. There is a IBM Systems blog all about FHE. There is a community. You can go for the premium edition of the toolkit, and you can contact Rohit here if you want to become a sponsor user of the program. So thank you. That's all I had to cover. You can scan this QR code if you want to connect with me on LinkedIn, and I will hand over to Kiwi and Anthony for the next part of the program.